Good morning to all of you. I welcomes to all in our lecture series on mechanics, that is your core paper 2, and we are discussing unit 4. The topic is oscillations. In our today class we are going to discuss about second part of your damped harmonic oscillation. In our first part we have been discussed up to this much. This is your general solution of damped harmonic oscillation. That is our equation number 13. In this part, we are going to discuss if B is greater than omega, then what will happen? B equal to omega or B less than omega. Three cases we are going to discuss. Then what type of physical behavior we can found from a damped harmonic oscillator or oscillation. Here B is nothing but belongs to your damping factor. From the beginning of our discussion I can show you now that I written that B, here B is nothing but belongs to damping constant, means belongs to resistive nature of the medium, or from where the oscillator getting the resistive, due to which its amplitude has to be decreased gradually with time. And omega is nothing but your natural frequency of the oscillator. So first case we are going to be consider if the resistive part is greater than that of the omega. So that means if B square greater than that of the omega square, then what will be happen? And this case is nothing but called as the over damping or heavy damping case. This case 1 is also called as over damping or heavy damping. First we have to consider this mathematical derivation, what we are going to get. You just watch it. In this case, if B square is greater than that of the omega square, then B square minus omega square will be the positive. Okay, because here B is greater than that of the omega, obviously B square minus omega square will be the positive, and hence B square minus omega square root over will be the real value and less than that of the B. Okay, therefore minus B plus B square plus omega square root over and minus B square minus omega square root over. Here it is minus, mistakenly written, it is plus. So hence minus B plus B square minus omega square root over and minus B square minus omega square B square minus omega square root over are both will be the negative. Okay. For that we can consider a simple example that you can consider B equal to 3, omega equal to 2. So B square equal to 9, omega square will be 4. Omega square will be 4. And 9 minus 4, that I am considering B square minus omega square. 9 minus 4 is equal to 5, and the root over here B square minus omega square root over will be 2 point something. So here minus B means minus 3 plus 2 point something will be the negative, minus B minus this 2 point something will be also the negative value. So this factor and this factor will be the negative. Now consider this factor. Here I mistakenly written B square minus omega square. This is B square minus omega square. So minus B plus B square minus omega square root over, let consider minus B1. Okay, and minus B square B square minus omega square. Mistakenly written, you just correct it. Okay, minus B plus B square minus omega square considered as minus B1, minus B square minus omega square root over is considered as minus B2. Now we have to substitute these two value in equation number 13. What we are going to get? First we have to consider the equation number 13. See, in equation number 13, e to the power minus bt is outside the bracket. If this e to the power minus bt, if I am going to take inside the bracket, then it will be add up. It will add up means it will be, see, e to the minus bt, here e to the power this much. So if I will take this term inside the bracket, then it will be minus bt plus this one, and here for this term it will be minus bt minus this term. Okay, so minus bt plus b square minus omega square root over t we have been considered as minus p1. So instead of this one we can write minus p1, and instead of this one we can write minus p2. Okay, so now equation number 13 will be, this is a by 2 will be outside, and we can get 1 plus b by omega square minus b square minus omega square root over into this much term will be written as e to the power minus p1t plus 1 minus b by b square minus omega square root over into e to the power minus p2t. Okay, let this is your equation number 14. See, this is our equation number 14. This is our equation number 14 we got by considering b square is greater than that of the omega square. By considering b square minus b square greater than that of the omega square, we found this equation. Means this is the displacement with time of the oscillator when resistive part of the medium is greater than that of the natural frequency. From this equation one can be perceive one thing, or one can easily understand that here a by 2 is the so called amplitude. Our amplitude is a, and this part is belongs to amplitude, and this first part and second part you can found this is one exponent to the power minus part is there, exponent to e to the power minus p1t e to the power minus p2t. That means due to this factor we know that exponent to the power e to the power minus x is always decreasing function. E to the power minus x is always decreasing function. Okay, that we know. This is your e to the power x, e to the x. This is your e to the minus x, e to the minus x. That means with increase of e to the, so e to the t, e to the minus t. So the increase of t, positive increase of t, this is decreasing function. So as these both two terms are decreasing, belongs to decreasing function, hence amplitude gradually decreases. Okay, same thing I have been written in the next page, that from equation number 14 it can be found that the displacement of the particle decreases with time. In this case the particle displaced from the mean position and returns to the mean position slowly without any oscillation. This type of motion is called as the overdamped or deadbeat, which is shown in the figure, this one. Okay, with time there is no oscillation, only the displacement is decreases slowly with time. There is without any oscillation. That means suppose you just imagine one thing, that suppose this is your pendulum. Okay, if we are going to take this pendulum from this to this side, and if we are going to leave, then it will oscillate like this, and slowly its amplitude is going to be decreased, and it has to be stop over here, but it is in the air medium, right? The same thing you just consider in a heavy medium. Suppose in a oil medium, suppose in a oil medium, if we are going to take this pendulum from here to this side, suppose with a small amplitude up to this much, and we are going to leave from here, then this bob is not going to be oscillate. It will just come to its mean position slowly without any oscillation. So if we are going to increase the resistive part of the medium, here if we are going to consider oil medium and air medium, Obviously oil medium have more resistive nature than the air medium. So hence, due to increase of resistiveness of the medium, the oscillation not happens. Only the amplitude decreases and stop at the mean position. Okay. So the physics, whatever we found from the we can derive, or what we understood from the mathematics, that is these things we have been discussed, and I also written. I suggest that you just pause the video and write the note which is most useful for your exam point of view. Okay, now we are going to be consider the second case when B equal to omega. This case is called as critical damping. Okay, so when B equal to omega, obviously B square equal to omega square. If now we are going to be derive the mathematics for this, if B square equal to omega square, then the solution belongs to equation number 8 could not be satisfied the equation number 4. Means if whenever B equal to omega, we could not say the equation number 8, that means this one, our general solution. From this we considered the boundary conditions, different boundary conditions, and we found A and B, and at last we got the equation number 13. That is okay, but it is our general solution of the damped harmonic oscillation. So when B equal to omega or B square equal to omega square, then we found A into e to the minus bt plus B into e to the minus bt, and that equation, that solution could not be satisfied the equation number 4, the differential equation 4. You can check in your rough that whenever B square minus omega square, then it will be how much? Xt will be A e to the minus bt plus B e to the minus bt. So this equation could not be satisfied the differential equation of a damped harmonic oscillation. So what we have to do? So to observe or to analyze this case, we just consider that B is slightly greater than that of the omega. That means B square minus omega square root over is equal to M, which is very small. M is very small. So to observe the mathematics, or to observe or to derive the mathematical derivations for this case, here we consider that not exactly B equal to omega, but B is slightly greater than omega, or we can say that equivalent to omega but greater than that of the omega, that I am going to say. So B square minus omega square root over will be the real, but it is very, very small quantity, okay, but not 0. Then equation number 8 will be, we are going to be put this value in equation number 8. What we are going to get here? In equation number 8, we can find minus B plus M into T, minus B plus M into T, A into plus B into e to the power minus B plus mt, minus B minus mt, minus B minus mt, right? I suggest to all of you that carefully watch and correct the notes wherever I am doing. Okay. So now xt will be equal to, take e to the power minus bt outside. So we can found a into e to the mt plus b into e to the minus mt inside the bracket, and we found that xt equal to e to the minus bt into a into 1 plus mt plus b into 1 minus mt, because we know that e to the power x is equal to 1 plus x square by 2 plus like that, or e to the minus x, if we are going to consider e to the minus x, it will be 1 minus x plus x square by 2 factorial, okay, plus like this. So this is the e to the x expansion, e to the minus x expansion. So instead of x, if we are going to consider mt, mt, then it will be 1 plus mt plus mt square by 2 factorial, like that. E to the minus mt, it will be 1 minus mt plus mt square by 2 factorial, like that, and so on. But higher torque we are not going to consider because m is very small. So mt square will be very small, again mt cube will be very small, very small. So this higher order terms of mt is not going to be considered. Only this first two term we are going to be considered. So instead of x we can write mt. So e to the mt will be 1 plus mt. Higher order terms are neglected, and e to the minus mt will be 1 minus mt by neglecting the higher order terms. So here higher power or higher order of mt are neglected because it is very small. Now we are going to be rewrite this equation in this format as xt equal to e to the minus bt into a plus b plus mt into a minus b. Okay, so consider a plus b equal to c and a minus b equal to d. So hence this equation can be written as x t equal to e to the minus bt into c plus dt, bracket closed. Let it is equation number 16. We have been considered that this is equation number 15, and let this is your 16 number equation. In this case, particle tries to reach its mean position more quickly than in case 1, as shown in figure this one. So here in this case what is happening? The oscillation is not going to happen, but the amplitude slowly decreases without any oscillation. Okay, when b is greater than omega, this case when b is equivalent to omega, then the decreasing time period is reduced. Means this amplitude that I am going to say that for this case, when b equal to omega, this amplitude suddenly decreases to its mean position. In your first case, for this first case b greater than omega, it decreases without oscillation, it decreases slowly towards the mean position. But in this case, omega b equal to omega, this amplitude suddenly decreases to its mean position. Okay, so with time the displacement is suddenly decreases. Means with a short time it come to its mean position, but this also same behavior, but it takes the long time as compared with this case. Okay, now we are going to consider when b less than omega. Here this case is resistive nature of the part of the medium is less than that of the frequency of the oscillation. What will happen? Let's see. So when b less than that of the omega, obviously b square less than that of the omega square, and this is called as under damping or small damping. Now in this case b square minus omega square will be negative because b is less than that of the omega square. So b square minus omega square root over will be written as minus omega square minus b square root over, because here omega is greater than that of the b. So minus omega square minus b square root over, or we can write I beta. Okay, this beta is nothing but omega square minus b square root over. Now equation number 8, what we can write? We have to move towards the equation number 8. Equation number 8, here instead of b square minus omega square root over, we can write I beta. For this case we can write I beta. Okay, because here omega is greater than that of the b, or omega square greater than that of the b square. So for this case, for the third case, this value, this value can be written as I beta. Okay. Now equation number 8 can be written as xt equal to a e to the power minus b plus I beta into t. So this will be minus b plus I beta into t, and this will be written as b into e to the minus b minus I beta into t. Okay. So this will be plus b into e to the power minus I beta into t. So e to the power I beta t can be written as cos beta t plus I sin beta t, and here e to the power minus I beta t can be written as cos beta t minus I sin beta t, right? So here you can see cos beta t is common factor we can get. So cos beta t into a plus b we can write with the simplification, and plus I sin beta t is the common in this case. Here you can see a I sin beta t, b minus b I sin beta t. So we can take common I sin beta t, then we can form a minus b. Let it is equation number this is your equation number 17. Just I simplified this one. Here cos beta t has taken common and we can get a plus b. I sin beta t can be taken common from this term and this term, we can get a minus b. Let it is equation number 17. Okay. Now put a plus b equal to r sin phi I into a minus b r cos phi. So r and phi are arbitrary constants here we have been considered. So the equation number 17 will be e to the power minus beta. Here you can see a plus b is considered as r cos phi. Okay, so cos beta into r cos phi plus sin beta into r sin phi. Okay, so this is e to the power minus beta. So the equation number 17 will be e to the power minus beta in minus bt into r cos beta into sin phi plus r sin beta into cos phi. See here a plus b is considered as r sin phi. Mistakenly I told at the time. So here a plus b is considered r sin phi. So here will be, instead of a plus b will be written as r sin phi. Here a minus b will be written as r cos phi. So cos beta into r sin phi, I sin beta into r cos phi. Okay. Okay. Now xt will be equal to r e to the minus beta into, this is sin a plus b into sin a minus b. So this r can be taken outside. This is sin a plus b formula. This means sin a into cos b plus cos a into sin b. So we can write sin a plus b, phi plus beta or beta t plus phi, no problem. So this is nothing but sin a plus b formula, or so we can write sin beta t plus phi. Let it is equation number 18. So here you can see that this is nothing but is our amplitude, initial amplitude of the oscillation, and this displacement is gradually decreases because the amplitude has been the factor with e to the power minus x. So with time increases, this is decreases, and another one oscillatory part is added in this term. Okay, so what will happen? That means it will be oscillate with time, but this amplitude is gradually also decreases. So in this case the motion will be oscillatory, but the oscillation is not simple harmonic. That means amplitude r is not remains constant. Simple harmonic means our amplitude always will be remain constant, but here amplitude is going to be decrease, because this factor due to the e to the minus bt factor, this amplitude is gradually decreases with time and with a oscillatory motion, because sine function is oscillatory. Okay, so up to this much we have to be stop over here. In the next class we are going to discuss time period, frequency, mean life and logarithmic decrement of this damped harmonic oscillation. So thank you so much for watching this video. You pause the video wherever you want. You write the note perfectly. If you have any doubt, you can ask me. We are going to discuss. Okay, so thank you so much. Thank you.